Picture this. It's a Tuesday morning. You've just arrived at work, coffee in hand, badge swiped, ready to do absolutely nothing remarkable with your day. Except your job isn't in an office. Your job is at a dinosaur park. And before you've even finished your first sip, your radio crackles to life with a voice that is trying very hard to sound calm and failing spectacularly. We have a situation at Enclosure 7. Enclosure 7 is the Tyrannosaurus rex habitat. 40 feet of reinforced steel, 20,000-volt electric fencing, motion sensors, pressure plates, and a moat that would make a medieval castle architect weep with pride. And somehow, the animal that was locked inside it last night is currently standing in the employee parking lot, staring at a Honda Civic with what can only be described as academic curiosity. You put down your coffee. You do not finish it. You will never finish it. This scenario, ridiculous as it sounds, is the entire thesis of one of the most entertaining thought experiments available to the human brain. Could we actually keep dinosaurs in captivity? Not just survive their existence, but manage it? Contain it? Run a functional facility where prehistoric megafauna are enclosed, fed, monitored, and presented to a paying public without anyone getting flattened, eaten, or legally liable for an extinction event? The question sounds like the setup to a movie you've already seen. But strip away the Hollywood drama and dig into the actual zoology, engineering, behavioral science, and logistics, and what you find is a problem of genuinely staggering complexity. Because keeping animals in captivity, even the ones we've been doing it with for centuries, is already incredibly hard. Scaling that challenge up to creatures that haven't existed for 66 million years introduces difficulties that range from logistically nightmarish to philosophically what are we even doing. So let's actually think this through. Seriously, all the way through. The first thing to establish is that captivity itself, even for animals we understand completely, is one of the most demanding tasks in applied biology. Modern zoos are not what they were 50 years ago. The concrete pit with a drain aesthetic that characterized 20th century animal keeping has largely been replaced by habitat-mimicking enclosures, enrichment programs, carefully managed social structures, species-specific diet protocols, veterinary care sophisticated enough to shame some human hospitals, and teams of behavioral specialists whose entire careers are devoted to understanding what a specific animal needs to not just survive, but maintain psychological health. And animals still escape. Animals still injure keepers. Animals still die from stress-related illness, from dietary deficiencies, from social isolation, from infections introduced by proximity to humans. Even with a century of accumulated knowledge about lions, elephants, gorillas, and polar bears, keeping them alive and healthy in artificial environments remains an ongoing challenge with no complete solution. Now take that challenge and apply it to animals for which we have zero captive management experience, behavioral data collected from living specimens, dietary intake records, social structure observations, or veterinary protocols. Animals for which every single piece of information we have comes from fossils, trace evidence, and inference. Animals whose biology we're still actively debating, whose precise physiology remains a subject of scientific disagreement, and whose behavior, in the absence of any living relative close enough to serve as a reliable behavioral model, is genuinely speculative in ways that would keep any responsible zoo director awake at night. That's the baseline difficulty. Before we've even discussed the size of these animals or the engineering required to contain them, the knowledge deficit alone is a problem of extraordinary magnitude. Start with diet, because feeding an animal is the most fundamental thing you do in captivity, and with dinosaurs, it immediately becomes a puzzle with missing pieces. Large theropod dinosaurs, the carnivorous ones, the spectacular, terrifying, crowd-drawing ones that every hypothetical dinosaur park would be built around, were apex predators consuming enormous quantities of meat. A full-grown T-Rex based on biomechanical models and comparison with modern large predators likely consumed somewhere in the range of 40 to 100 kilograms of meat per feeding, with feeding frequency that probably wasn't daily. So far, so manageable. Large carnivore facilities already deal with bulk meat acquisition, and scaling up the quantities is inconvenient rather than impossible. The problem is deeper than quantity. Modern carnivore diets in captivity are carefully formulated to replicate nutritional profiles that the animals evolved to consume. Lions get supplemented with the nutrients found in organs and bone marrow. Birds of prey receive whole prey items specifically to provide dietary variety and enrichment. Getting the micronutrient balance right is already finicky for animals whose ancestors we can study in the wild. With carnivorous dinosaurs, we don't know the precise nutritional composition of their natural prey. We don't know what trace elements their metabolism specifically required. We don't know if they had dietary preferences between different prey species, or whether certain nutrients in certain prey items were critical for bone health, reproductive function, or immune maintenance. Feeding a T-Rex beef from a modern cattle operation might be like trying to sustain a lion exclusively on protein powder. Technically caloric, but missing something essential that you won't realize is missing until the animal starts showing deficiency symptoms that no veterinarian has ever seen before. Herbivorous dinosaurs present equally daunting problems. The plant ecosystems of the Mesozoic era were dramatically different from anything alive today. The ferns, cycads, and primitive conifers that dominated Jurassic and Cretaceous landscapes had different biochemical profiles, different fiber compositions, different nutrient densities than modern vegetation. Sauropods, the enormous long-necked giants, were processing plant matter through digestive systems specifically adapted over millions of years to those specific plant types. Whether their gut microbiomes, digestive enzymes, and metabolic systems could handle modern vegetation is completely unknown. They might be fine. They might develop chronic digestive dysfunction within months. There is no way to know in advance. Enclosure engineering is the next mountain, and it is, depending on which dinosaur you're discussing, either a very large mountain or an almost vertical wall. Begin with the sauropods because they are the most immediately size challenging. Argentinosaurus, potentially the largest land animal that ever lived, may have reached lengths of 30 to 40 meters and weights of 60 to 100 tons. For reference, a fully grown African elephant, the largest living land animal, reaches about 6 tons. The largest enclosure ever built for an elephant at a modern zoological facility is roughly a few hectares. Scale that proportionally to an animal 15 times heavier and metabolically active at a completely different order of magnitude, and you're describing a land area that begins to resemble a small county rather than a zoo exhibit. The structural engineering of barriers for sauropods is almost comedic in its demands. An animal weighing 60 tons pushing against a barrier generates forces that no standard zoo fencing can begin to address. You'd need reinforced concrete walls of enormous thickness, anchored to foundations deep enough to handle dynamic loading from an animal that treats your life's work as a mild inconvenience. The cost of constructing even a single adequate sauropod enclosure, if such a thing were even theoretically possible, would likely dwarf the GDP of a small nation. Now, pivot to the animals that most people are actually interested in, the large theropods. T-Rex is the obvious centerpiece. And let's be specific about what T-Rex was. An adult Tyrannosaurus rex stood approximately 4 meters at the hip, stretched 12 to 13 meters in length, and weighed somewhere between 8 and 14 tons depending on the individual and the estimate. It possessed the strongest bite force of any terrestrial animal ever measured, estimated at around 35 to 60,000 newtons, and was capable of crushing through bone as a routine feeding behavior. Its legs were powerful enough to sustain locomotion at speeds researchers have variously estimated between 12 and 25 kilometers per hour, though the upper end of that range remains debated. To contain an animal with that physical profile, you're not building a fence. You're building a fortress. Walls would need to be tall enough that a bipedal animal 4 meters at the hip can't simply place its forelimbs on top and push. They'd need to be strong enough to withstand repeated impact loading from an animal weighing 10 tons. Any gate or access point would need to be engineered with redundant locking systems capable of resisting that bite force, because an animal that can crunch through bone for breakfast will not be deterred by a standard padlock. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more, plus an exclusive PDF guide included. Link in the description. See you inside. Electric fencing, which is a standard tool in modern large carnivore management, would need to deliver shocks powerful enough to aversively condition an animal with a nervous system scaled to a creature of that size. What voltage deters a T-Rex is something nobody alive has any data on, and the trial and error phase of that research is not something any responsible facility manager wants to be responsible for. Behavior is where the entire thought experiment becomes philosophically interesting in ways that go beyond pure engineering. Animal captivity works when it works because we understand, at least partially, what the animal needs, what stresses it, what stimulates it, and what pathological behavioral signs look like when something is wrong. Decades of field study on lions, great apes, cetaceans, and elephants have produced behavioral baseline data that allows zoo professionals to recognize when an animal is thriving versus when it's deteriorating and to intervene accordingly. For dinosaurs, that baseline doesn't exist. Every behavioral assumption would be inference layered on inference. We know from trackways that some large theropods moved in ways consistent with some degree of social tolerance, multiple individuals traveling in what appear to be coordinated directions. We know from nesting sites that certain dinosaurs showed parental investment behaviors. We have evidence from bone analysis that some species had complex social lives, but the granular behavioral detail that captive management requires. How does this animal signal distress? What triggers aggression between individuals? How much space does it require to avoid psychological deterioration? What enrichment activities maintain cognitive engagement? None of that is available. The captive behavioral pathologies we see in modern large predators, repetitive pacing, self-directed behaviors, aggression toward keepers, emerge from unmet behavioral needs that took decades to identify and partially address. With dinosaurs, those pathologies would be unrecognizable until they'd progressed to a point where the consequences were severe. An elephant in psychological distress is dangerous. A 10-ton theropod in psychological distress is a catastrophe that no enclosure wall was actually designed to contain. The question of intelligence deserves its own careful examination, because it substantially changes the containment calculus. Modern paleontological consensus has moved significantly away from the dinosaurs were slow, stupid lizards narrative that dominated popular imagination for most of the 20th century. Evidence from encephalization quotients, brain size relative to body size, suggests that at least some theropod lineages had cognitive complexity substantially beyond what a simple reptilian model would predict. The small dromaeosaurids, Velociraptor and its relatives, had brain-to-body ratios comparable to some modern birds, which, given that modern birds are the direct living descendants of theropod dinosaurs, is perhaps unsurprising. And modern birds are smart. Crows solve multi-step problems. Ravens demonstrate planning behavior. Parrots manipulate social situations. If the small dromaeosaurids had comparable cognitive capacity to corvids or psittacines, then keeping them in an enclosure requires not just physical containment, but intellectual containment, an environment complex enough to prevent the problem-solving behavior that boredom and intelligence produce in combination. Clever animals escape. Every zoo professional knows this. Primates dismantle latches. Octopuses open jars and navigate obstacle courses. Crows remember individual human faces and hold grudges. An animal with corvid-level intelligence and raptor-level physical capability, contained in an enclosure designed by people who underestimated its cognitive capacity, is not a containment success story. It's a countdown. T-Rex, interestingly, had a relatively larger brain than many other large dinosaurs, with olfactory bulbs suggesting particularly acute smell, potentially comparable to modern birds like vultures that locate food primarily by scent. Whether this translated into behavioral flexibility and problem-solving capacity is unknown, but it's worth noting that the animals most capable of locating hidden food sources in the wild tend to be the ones most capable of locating weaknesses in captive environments. Health and veterinary care represent another dimension of the problem that is easy to underestimate until you think it through carefully. Modern zoological veterinary medicine is remarkable. Veterinarians perform surgery on great apes, treat respiratory infections in big cats, manage reproductive health in elephants, and develop pharmacological protocols for animals whose physiology differs significantly from the domestic species that veterinary training originally focused on. But all of this is built on research, observation, and accumulated clinical experience with living animals. Treating a dinosaur would mean starting from zero, no established drug dosages, no known anesthetic protocols. And anesthesia is critical because you cannot perform any medical procedure on a conscious large theropod and expect anyone to survive the experience. The pharmacokinetics of any sedative in a dinosaur's metabolism are completely unknown. Too little, and the animal isn't adequately sedated. Too much, and you've accidentally killed the most expensive and scientifically significant animal on Earth. Getting the dosage right requires data that doesn't exist and can only be generated by experiments that are, by definition, dangerous. Parasitology is another unexplored dimension. Dinosaurs would have carried parasites, internal and external, specific to their species and their era. Some of those parasites might not have survived in the modern environment. Others might find modern hosts with no evolved resistance and no immune defenses. The ecological consequences of introducing Mesozoic parasites into modern ecosystems through a captive dinosaur program are difficult to predict and could range from trivial to genuinely catastrophic. Immune function is similarly uncertain. Dinosaurs evolved in an environment with different pathogen pressures than the modern world. Modern zoonotic diseases, bacteria, viruses, fungi that circulate in contemporary animal populations, might be devastating to animals with no evolutionary exposure to them. The reverse concern is equally valid. What pathogens might dinosaurs carry that modern mammals and birds have never encountered? Biosecurity protocols for a captive dinosaur facility would need to address threats from both directions simultaneously. There's a social dimension to captivity that often gets overlooked in the engineering discussion, and for some dinosaurs, it might be the hardest problem of all. Evidence increasingly supports that many dinosaur species were social to varying degrees. Hadrosaurs, the large duck-billed herbivores, appear to have nested colonially and may have traveled in herds. Ceratopsians like Triceratops have been found in bone beds suggesting group living. Even some large theropods show evidence of social tolerance beyond simple mating interactions. Social animals in captivity require social management. Keeping a single individual of a highly social species produces isolation stress that manifests in behavioral pathology, regardless of how well designed the physical enclosure is. Keeping multiple individuals requires understanding dominance hierarchies, reproductive dynamics, aggression triggers, and the spatial requirements needed to maintain stable social groups without chronic conflict. For dinosaurs, that social data is almost entirely absent. You'd be navigating social management for a species whose social structure you can only partially infer from trace fossil evidence, in real time, with consequences for getting it wrong measured in tons of muscle and bone. The breeding question is equally complicated. Captive populations of endangered species are maintained through carefully managed breeding programs that balance genetic diversity, reproductive compatibility, and population demographics. For a captive dinosaur population brought into existence through some hypothetical de-extinction process, the initial genetic diversity of the founding population would determine the long-term viability of the captive program. Too little genetic variation and inbreeding depression would compromise health and fertility within generations. The atmospheric and environmental context is something the popular discussion almost never raises, and it's one of the more fascinating scientific wrinkles in the entire problem. The atmosphere of the Mesozoic era was different from today's. Oxygen levels during parts of the Cretaceous period were somewhat higher than present. Estimates vary, but the difference may have been meaningful for animal physiology. Carbon dioxide concentrations were substantially higher, contributing to warmer global temperatures and different patterns of humidity and precipitation. The overall climate was more uniformly warm and humid than modern Earth's latitudinally stratified climate zones. Whether dinosaur physiology was specifically adapted to those atmospheric conditions in ways that would create health problems in modern atmospheric composition is a genuinely open question. Modern birds, theropod descendants, function perfectly well in current atmospheric conditions, which provides some optimism. But modern birds have had 66 million years of selection pressure to adapt to atmospheric change. A de-extincted dinosaur with Cretaceous-era physiology hasn't had that time, and the potential for atmospheric mismatch to create subtle physiological stresses is real. Temperature management would be a significant operational consideration. The consistent warmth of the Mesozoic suggests that large dinosaurs were accustomed to thermal environments substantially warmer than what most of the inhabited world currently offers. Facilities in temperate climates would need climate control systems operating at an enormous scale to maintain appropriate thermal environments in enclosures large enough to house multi-ton megafauna. The energy costs alone would be staggering. Step back from the individual challenges and consider the systemic picture, because there's something important that emerges when you look at all of these problems together. Every individual challenge, diet, containment, behavior, veterinary care, social management, atmospheric conditions, is a problem operating under conditions of profound uncertainty. And uncertainty compounds. When you have one unknown variable in a system, you can manage around it. When every variable in the system carries significant uncertainty, the interactions between those uncertainties produce outcomes that are not just unpredictable but genuinely unmanageable with any reliability. Modern zoos work because they've reduced uncertainty progressively over decades. Every generation of keepers learns from the previous one. Protocols are refined. Behavioral baselines are established. Veterinary knowledge accumulates. The system becomes more predictable over time as the knowledge base grows. A dinosaur captivity program would be starting that process from scratch, with animals whose failure modes are far more consequential than anything in the existing body of zoo management experience. The liability picture, if you want to think about it in purely practical human terms, is extraordinary. A facility operating captive T-Rex specimens would be assuming responsibility for outcomes that no existing legal, insurance, or regulatory framework is remotely equipped to address. The risk modeling alone would require creating entirely new actuarial categories. Underwriters who comfortably price policies for facilities keeping lions and tigers would take one look at the specifications for a large theropod enclosure and retire on the spot. And yet, and this is the part that makes the thought experiment worth having, humans have an almost unbroken record of doing things that experts said were impossible, inadvisable, or catastrophically dangerous, and then doing those things anyway, sometimes successfully. We keep animals in captivity that would have seemed inconceivable 2 centuries ago. White sharks were for decades considered impossible to maintain in aquaria. Too large, too sensitive, too dependent on continuous forward movement for gill ventilation. The Monterey Bay Aquarium succeeded, briefly with juvenile individuals, before releasing them. The knowledge generated from those attempts informed everything that came after. Captive killer whale programs, despite their profound ethical problems and operational failures, generated behavioral and physiological data about cetaceans that couldn't have been collected any other way. The history of zoological science is a history of attempting things that seemed impossible, failing instructively, revising approaches, and occasionally succeeding in ways that changed what everyone thought was achievable. If dinosaurs somehow existed in the modern world, the first attempts at captive management would almost certainly be disasters. Animals would escape, people would be hurt, enclosures would fail in ways nobody anticipated. But the knowledge generated from each failure would accumulate, and over time, what started as a chaotic nightmare might evolve, slowly, expensively, at significant human cost, into something approaching a functional science of dinosaur husbandry. The question, could humans keep dinosaurs in captivity, might ultimately have the same answer as, could humans fly? Or could humans transplant a heart? Not right away, not without catastrophic early failures, not without developments in knowledge and technology that didn't exist at the time the question was first asked. But eventually, given enough time, enough incentive, and enough of what might generously be called catastrophic trial and error, probably yes. The ethical dimension is the final layer that nobody who thinks seriously about this question can avoid. Captivity, even for well-managed modern species, raises genuine welfare concerns that the zoological community has been grappling with honestly for decades. The consensus has shifted substantially toward viewing captivity as justifiable primarily in the context of conservation, maintaining populations of endangered species, supporting reintroduction programs, funding field research. The animals exist for human entertainment. Rationale has become increasingly difficult to defend as our understanding of animal cognition and emotional complexity has deepened. For dinosaurs, the ethical calculus would be extraordinary. Bringing an animal into existence through de-extinction, specifically for the purpose of captive display, in an environment incompatible with its evolutionary history, in conditions no keeper fully understands, surrounded by pathogens its immune system never encountered, fed food its metabolism wasn't adapted to, enclosed by barriers that constrain behavior in ways nobody can quantify. The welfare implications of that are not comfortable to sit with. These aren't hypothetical concerns. They're the same concerns being raised about existing captive programs for elephants, great apes, and cetaceans, and those conversations have already changed how those programs operate. A captive dinosaur program would inherit all of those ethical tensions, amplified by the additional layer that the animals in question would exist in the modern world entirely because humans chose to create them for human purposes. Whether that's justifiable is not a scientific question. It's a moral one. And the honest answer is that humans haven't finished working out the answer even for the species already in our care. So circle back to Enclosure 7. The Tyrannosaurus rex is still in the parking lot. It has lost interest in the Honda Civic and is now regarding the building where you're hiding with the calm, evaluative attention of an animal that has never, in its evolutionary history, had a reason to feel threatened by anything. The enclosure that was supposed to contain it was designed by the best engineers money could hire, informed by every piece of paleontological data available, built to specifications that exceeded anything in the existing zoo management literature. And here we are. Could humans keep dinosaurs in captivity? Maybe, eventually, after a great deal of learning that nobody would enjoy. The engineering is probably solvable, given sufficient resources and motivation. The behavioral science would develop, painfully and slowly, from experience that would be unpleasant to accumulate. The veterinary protocols would be established over time by professionals with extraordinary dedication and presumably very good life insurance. But eventually possible with sufficient catastrophic trial and error, and should we do this are different questions. And looking at the 10-ton apex predator calmly assessing your structural choices from the parking lot, the second question feels significantly more urgent than the first. Your radio crackles again. The voice is now not trying to sound calm at all. It's figured out the side gate. You didn't finish your coffee this morning. Looking back, that seems like the least of your problems.